Hi again, everybody. This is another unit in our module on climate and the influence of climate on our plant choices. In this unit, we're going to look at plant adaptations to heat and drought, which will then help us select and maintain plants that are appropriate for our climate. By the end of this unit, you'll be able to describe plant adaptations to heat and drought, and also describe ways in which some adaptations to heat and drought can be used as ornamental characteristics in a cultivated landscape. You'll remember from the previous unit on climate that most of California has a Mediterranean type climate, which is typified by warm or hot dry summers and mild wet winters. Accepting and understanding our pattern of rainfall is a key component in selecting plants that are appropriate for our region. The graphs on the right show the average monthly rainfall throughout the year in Santa Cruz, Monterey, and San Diego. And you can see in these graphs the pattern of rainfall that's typical of a Mediterranean type climate. So here and here, the rainfall peaking in the winter and dropping off in the summer. As you can also see from the graphs and the figures below, the amount of annual rainfall differs widely between San Diego and the Monterey Bay. And you may remember me mentioning in an earlier unit that rainfall decreases as we move from south to north through California, and also from west to east as we move away from the coast. What may be surprising to you is that the average annual rainfall in London, in England, is less than what we usually have here in Santa Cruz. The big difference between these two locations, though, is the pattern of rainfall. In the UK, which has a temperate climate, annual rainfall is distributed relatively evenly throughout the whole year, whereas, as we've already mentioned, California's is usually limited to about 5 months from late November to late April. In Bob Perry's 1992 book, Landscape Plants for Western Regions, he writes that sustainability in an ornamental landscape begins with a strong relationship to the nature of its region. The main factor influencing the nature of our region is, of course, our Mediterranean type climate with its long dry summers. But part of the nature of our region here in California is also the unreliability of our water supply and our historic overuse. We sometimes have sustained periods of drought that can last for several years. And depending on where we live, some of our aquifers are overdrafted and some have saltwater intrusion, especially here in the Pajaro Valley and also within the Soquel Creek Water District. The history of California's water usage and water rights is complex and beyond the scope of this class. But for any of you interested in learning more about this topic, I highly recommend Cadillac Desert and An Introduction to Water in California by David Carl. In recent years, landscape use of water has been a very visible target of water conservation measures in California. But research in 2015 by Donald Hodel and Dennis Pettinger from University of California Cooperative Extension found that the landscape use of water in California accounts for just 9% of the state's total water usage, as you can see in the diagram on the right here. Given this small percentage, it's impossible for landscape irrigation conservation alone to solve California's water supply problems. However, that doesn't mean that horticultural professionals and home gardeners should ignore the problem, or that we shouldn't build climate resilience into our landscapes. And we can do that in several ways. Firstly, it's estimated that lawns account for between 40 and 60% of landscape irrigation use. So one step we can take is to reduce the area of our landscapes that are planted with lawn. We can also eliminate unused lawn areas and replace them with low water use plants, which would also have the added benefit of enhancing wildlife habitat. Or we could just replace unused lawns with mulch. We can also learn how to irrigate our plants correctly, and this means applying only the amount of water that plants need to perform well and not overwatering them. And we can also incorporate plants with low water requirements into any new plantings and try to replace dead or underperforming plants with ones that are more water-wise. So on that note, let's take a look at some of the adaptations plants have to heat and drought. Plants exhibit several adaptations to heat and drought, and sometimes individual species exhibit more than one adaptation. But in general, we can classify the plant adaptations into three categories: physical, physiological, or a combination of the two. And we're going to have a look at most of the main adaptations now. The internal structure of succulent leaves is modified so that it retains more water than the leaves of non-succulent plants do. This adaptation involves large, thin-walled parenchyma cells that don't have chloroplasts, that are just to the inside of the epidermis. These cells are non-photosynthetic, and they contain large vacuoles that hold relatively large amounts of water. Examples of succulents are agaves, or most agaves, aloes, cotyledon, echeveria, and some of the euphorbia species. Cacti are succulents that have leaves modified as spines. The reduction in leaf surface reduces water loss from these plants. True spines are modifications of the whole leaf, and most of the normal leaf tissue is replaced with sclerenchyma. And photosynthesis in these plants occurs in the stems. Examples that are familiar to us are prickly pear and barrel cactus and the saguaro cactus. Sticking with the spiny leaf adaptations, a dense coating of spines can also provide some shade for the stem by day and act as insulation by night. Remember that some deserts can experience sub-freezing temperatures in the winter. An example of this would be the teddy bear cholla. Spines can also diffuse light, ensuring that light is distributed over the plant's entire surface area, and this can help improve photosynthesis. Cactus spines can also collect water. The spines on some species are curved downwards, so that any water landing on them will drip onto the soil immediately above the roots. And a good example of that is this red spine barrel cactus, pictured here on the right. Some cactus spines have a cork-like texture that absorbs water, and nothing really to do with heat and drought, but spines can also provide protection sometimes from grazing animals. Leaves arranged spirally in a dense rosette are common in water-wise plants, and this arrangement helps direct water straight to the roots. Water landing on the rosette spirals its way downwards through the foliage and trickles down the stem to the roots. Plants in both hot and cold climates often accumulate waxes on their leaves or on their needles. These waxes are often shiny and are thought to prevent water loss and reflect light, which keeps the leaf temperature from becoming too hot. The waxy cuticle also provides insulation in freezing winter temperatures. Some plants also develop a waxy, powdery coating on the leaves which reflects sunlight, and an example of this would be pig's ears, Cotyledon orbiculata, and our native succulents, species in the genus Dudleya, and you've got our locally native Dudleya cespitosa, pictured here on the right. Plants that have leaves with a whitish waxy cuticle are described as being glaucous. Having a large leaf surface area can be detrimental to plant growth and survival under conditions of water stress because there's more surface area from which water can be lost. Therefore, having really small or narrow needle-like leaves with a small surface area can be advantageous. Examples would be many of the conifers with needle-like leaves, such as our coast redwood, English yew, and other examples would be lavender, rosemary, and the Australian shrub woolly grevillea, Grevillea lanigera. Drought stress isn't limited to plants in areas of low precipitation and high heat. Drought stress can also occur in winter in areas where the ground is frozen and there's no liquid water available for the roots to take up. Many conifers that are native to subalpine and alpine areas share some of the leaf adaptations to drought that we see in desert and sclerophyll shrubs and trees. They have sunken stomata and a thick waxy cuticle, which is a layer of thick-walled cells just beneath the epidermis. As mentioned in a previous unit on climate, the 5 regions of the world with Mediterranean-type climates each have a typical plant community that shares similar characteristics. In California, this plant community is called chaparral. In the Mediterranean basin, it's called maquis or garrigue. In South Africa, it's fynbos. In Australia, mallee, and in Chile, matorral. Many plants in these communities have what are referred to as sclerophyll leaves. And this comes from the Greek words sclero and phyll, meaning hard leaf. Examples include manzanitas in California, proteas and leucodendrons in South Africa, and eucalyptus and banksias in Australia. If you touch the leaves of these plants, they feel hard and thick and leathery, and you'll see that they feel much thicker than the leaves of deciduous plants. Sclerophyll leaves are typically about 3 times thicker than those of deciduous species. They're evergreen, and the leaves are longer lived than the leaves of non-sclerophyll evergreen species, often living up to 2 years. And this is a way of conserving energy. The leaves tend to have a high fiber content and often produce aromatic oils. And the evaporative heat loss when these oils volatilize reduces the leaf temperature and therefore water loss. Examples of sclerophyll plants with aromatic leaves are lemon bottlebrush, which is pictured here on the right, and eucalyptus. Compared to non-sclerophyll plants, sclerophyll shrubs and trees also have differences in their stomata that help to conserve water. The stomata are typically smaller, and they tend to be concentrated on the lower leaf surface as opposed to both upper and lower leaf surfaces. And they're also often sunken in pits or grooves. Some plants orient their leaves in a near vertical position to the sun, which decreases their direct exposure to sunlight and in turn keeps the leaf surface cooler. A good example of this would be the manzanita, pictured here on the right, the bigberry manzanita, Arctostaphylos glauca. And an example from South Africa would be Leucospermum, the pincushion bush. Many plants have hairy leaves which reduce water loss by reducing the wind speed over the leaf surface. The hairs trap moisture, and silvery white hairs also reflect sunlight and help to keep the leaf surface cooler. Examples include woolly grevillea, Grevillea lanigera, Spanish lavender, lamb's ear, Jerusalem sage, and woolly thyme. Grey or silver leaves reduces water loss by reflecting solar radiation, which helps to keep the leaf surface temperature much cooler. And examples that we would see around here quite often include Spanish lavender, English lavender, and if we're out hiking, the bonny doon manzanita, Octostaphylos sylvicola. Sometimes just one surface of the leaf is grey or silver, and an example of that would be Diamondia margaritae, just Diamondia, which is pictured here in the photo on the right. A couple of other examples would be our California native coast silk tassel, Garrya elliptica, and coast buckwheat, Eriogonum latifolium. Some plants have leaves which curl inwards or under at the leaf margins in response to heat and drought stress. Downward curling reduces water loss by protecting and shading the stomata. And an example of a plant that does this would be the coast silk tassel, pictured here on the right, Garrya elliptica. Upward curling is often seen in plants which have a silver-green leaf underside, and the curling exposes the lighter colored surface to the sun. In some plants, there are specialized cells called bulliform cells, and we see these quite frequently in monocots such as grasses and the Australian herbaceous perennial Dianella. And these bulliform cells causes the leaves of these plants to roll inwards. Some plants have dimorphic leaves. Dimorphic means two shapes, and it refers to plants that have two sets of differently shaped or sized leaves as their adaptation to heat and or drought. A couple of examples of this would be our California native sage, the purple sage, Salvia leucophylla, or the European Phlomis fruticosa, Jerusalem sage. Both these plants have a set of smaller leaves and a set of larger leaves. At the beginning of summer, as temperatures start to warm up, the larger set of leaves is dropped in order to conserve water and energy, leaving the smaller leaves on the stems through the hot, dry months to continue photosynthesizing. A new set of larger leaves is then produced when temperatures cool down in the winter and the rains have started. Some plants survive drought by dropping their leaves completely in response to summer heat and drought. An example would be our California native deerweed, Acmispon glabra. California buckeye, Aesculus californica, drops its leaves completely in areas which are warmer in the summer. Up in the Sierra, it tends to keep its leaves through the summer. Some plants have thick, fleshy roots that store carbohydrates and water. And an example of this would be the African pelargonium, pictured here on the right. Some plants employ a dual water-seeking strategy with their roots. For example, when the seed of some of our native oaks germinates, the seedlings rapidly develop a large, long taproot, often several weeks before the shoot emerges above ground. That taproot is able to seek out water sources deep in the soil profile, which then provides water to the shoot as it emerges above ground and continues to grow. As the young plants continue to grow, they develop a mat of finer roots closer to the soil surface, which are able to take advantage of the winter rains very quickly when they come in the fall. The taproots of the 4 California native oaks listed below can reach as much as 70 feet below the soil surface. Geophytes are plants that die back to an underground storage organ in order to avoid environmental stresses such as drought or cold. And geophytes can be classified according to the plant part that acts as the storage organ. So we have bulbs like daffodils and tulips and naked lady, corms like diorama and watsonia, which are both native to South Africa, rhizomes, which are stem-like structures which are usually just below the soil surface, and our native Douglas iris, Iris douglasiana, would be an example of this. And then tubers, such as dahlia. These aren't drought tolerant, but for them, the tubers would be an adaptation to winter cold. Another adaptation to heat and drought is just to have a really short life cycle. Annuals are more abundant in Mediterranean climates than any other climate type, and they're particularly abundant in California, where around 30% of our native plants are annuals. The strategy here is avoiding both heat stress in the summer and, in cold climates, avoiding cold stress in the winter by having a really short life cycle. Physiological adaptations include a slowing down of physiological processes in summer, or going summer dormant. Many plants in chaparral-type plant communities retain their leaves through the dry summer months, but they slow down their photosynthesis and the rest of their physiological processes. Their stomata are closed for longer periods of time in order to conserve water, and that's why photosynthesis is limited and therefore growth is limited during the hot summer months. Other physiological adaptations include alternative paths of photosynthesis, such as C4 photosynthesis and CAM photosynthesis, the cressolation acid metabolism pathway. And both of these are looked at in the Introduction to Horticulture class, Hort 1A. So let's look now at how we can use some of these adaptations to heat and drought in our plant selections, plant maintenance, and our design. Knowing what plants' physical adaptations to heat and drought are can really help us as horticultural professionals and enthusiastic home gardeners. Firstly, it can help us choose climate-appropriate plants. We can use California natives from ecosystems with climates similar to the one in which we're creating a landscape. We can also use plants from other Mediterranean-type climates that are similar to ours, or we can look to ecosystems that are more extreme in terms of heat and drought, such as desert ecosystems. For some plants, knowing what their adaptations to heat and drought are helps us with irrigation requirements, and particularly troubleshooting when plants appear stressed or even die. Plants that exhibit physiological dormancy as their adaptation to heat and drought usually require little or no summer water, and providing supplemental summer water can actually shorten their lives. Supplemental summer water can also promote root rots caused by fungal and water mold pathogens. And plants that are particularly vulnerable to this are our native coast live oak, Quercus agrifolia, Matilaha poppy, and California flannelbush, the Fremontodendrons. Some plants have obligate summer dormancy, and no matter how much summer water we give them, they won't stay green and they won't retain their foliage. And applying summer water to these plants that absolutely have to go summer dormant will almost always result in root rot and death. A good example of this is our native fern that's pictured on the right of this slide, the California polypody, Polypodium californicum. Some adaptations to heat and drought can give us visual indicators of drought stress and can be used to tell us when to irrigate. For example, the inward leaf rolling in some of the monocots and the loss of lower leaves in plants like island mallow, pictured here on the right, are good indicators that it may be time for us to give the plants some more water. Production of a taproot can be indicative of a species that is hard to transplant once it's established, or of a plant that doesn't like its roots disturbed when it's being planted. Good examples of this would be the island bush poppy, pictured here on the right, and two of our native lupins, the bush lupin, Lupinus arboreus, and the silver bush lupin, Lupinus albifrons. These are plants that we should take great care with if we're trying to transplant them, and plants whose roots we really shouldn't disturb too much when we're planting them out from containers if we've just bought them from a nursery. I mentioned earlier that the leaves of sclerophyll shrubs are typically longer lived than non-sclerophyll shrubs. So one advantage of this is that it can result in less leaf litter. So this could mean that sclerophyll shrubs are particularly suited for a client who's averse to leaf litter on a path or driveway, and they might suit a client who's looking for low maintenance plants. On the right here, there's a picture of the hybrid manzanita, the sentinel manzanita, planted in a location where the lack of leaf litter might be an important consideration. The tough, fibrous leaves of sclerophyll plants and highly aromatic leaves and very hairy leaves all tend to be fairly unpalatable to deer. So plants with these adaptations to heat and drought are going to be good selections in areas where deer are a problem. Plant adaptations to heat and drought are obviously important survival mechanisms for plants in their natural habitats, and they can also help us create more sustainable, low-water planting schemes. But we can also highlight some of these adaptations as ornamental characteristics to enhance our planting schemes. So the last few slides in this unit are going to take a quick look at some of the ways in which we could do that. Firstly, we could take advantage of the ornamental aspect of bifacial leaf color and leaf rolling. For example, the bifacial leaves of Diamondia and rosy buckwheat, pictured here on the top right, can add extra color dimensions to a landscape. Here's a slide showing the rosy buckwheat, Eriogonum grande rubescens, again in full bloom in a Bay Area landscape. This landscape was designed and installed by East Bay Wilds. And this vignette from that small front garden shows just a glimpse of that silvery underside of the leaves on rosy buckwheat. And you can see that it's also tying in nicely with the color selection of the pavers that are around this planter bed. Ocotillo may lose its leaves in response to drought, but it still makes a really dramatic architectural statement. And the shadows of its silhouette on the wall of a house also look particularly dramatic. Here's another really dramatic plant, a close relative of the Ocotillo, shown on the previous slide. So how about adding a touch of cool and unusual to a planting scheme? This Fukiaria is the bujum tree, native to the Baja Peninsula and northern Mexico. And it has a swollen, fleshy trunk and looks very Dr. Seussish or prehistoric. But this is a plant that you rarely see in an ornamental landscape, so it might be a good one if you're looking for something cool and unusual, or you want to add a talking point to a planting scheme. Although the challenge here would be finding a nursery that's actually growing this plant. A dense covering of hairs provides some cacti with insulation from both heat and cold and diffuses the light. From an ornamental point of view, the light plays off the fine hairs, creating a beautiful halo effect, which can be really quite dramatic when the plant is backlit. The fiery pinkish-red thorns of this Mexican fire barrel cactus add a dramatic splash of color to an ornamental landscape, either in the ground or in a container. And the thorns here look particularly dramatic in contrast to the yellow stripes on the variegated century plant in the background. And how about turning your hand to bonsai with some of the arborescent succulents? This is a maiden's quiver tree from South Africa, where in its natural habitat it grows to about 6 to 7 feet tall in the ground. But in this bonsai at the Desert Botanical Garden in Phoenix, it's maintained at around 15 inches tall. And check out the interesting texture of its stem, as well as the skill of the bonsai. We can also incorporate some plants with heat and drought adaptations into our edible landscapes. The picture here is of prickly pear, which you see fairly frequently here in Santa Cruz and Monterey counties. The fleshy fruit on this cactus are juicy and edible, but be careful picking them and make sure you peel them thoroughly before eating them. The fleshy pads are also edible and called nopales in Mexican cuisine. Again, pick the pads carefully and make sure you peel them thoroughly before eating them. Prickly pear and many other plants with vicious thorns or prickles also make good burglar deterrents. The volatile oils in many of the herbs and spices that we use for cooking are also adaptations to heat. So examples would be rosemary, sage, oregano, marjoram, and lavender. Finally, let's do a quick summary of this really long unit. Plants exhibit many adaptations to heat and drought, including physical and physiological adaptations, and sometimes combinations of the two. Some adaptations to heat and drought also provide plants with protection in freezing winter temperatures. As horticultural professionals and amateurs, we can use these adaptations to help us with plant selection, plant maintenance, and design in our landscapes. If we own a nursery, we could also grow some of the more unusual drought-adapted plants to help diversify our product line and help differentiate us from some of the larger, more mainstream nurseries. So after this long unit, go take a break now, and then when you have time, come back to Canvas and take the quiz on plant adaptations to heat and drought.